Okay, welcome to this seminar talk. And the plan of this talk is to give a kind of executive summary of my course currently running at ETH Zurich. This is a 4-hour per week course, which I have to give via Zoom because Vienna was getting red on the Ampel at the time when I was supposed to move, and now I'm happy to be here at home. So the topic will be, roughly speaking, an elementary approach to what I call, meanwhile, mild distributions. And I will try to explain to you what it is and how to use it. And as my friends are always saying, you have to see my favorite slide. Here it is, right at the beginning. It's about the zoo of function spaces that people encounter when they are doing Fourier analysis. So very often you start with the blue object, which is L1, because it's so natural to define the Fourier transform on the L1 case. Then you need L2 for proving Plancherel's theorem. You want to show that Fourier transform is giving you C0 functions, so functions vanishing at infinity. So in my picture, it means you rotate the blue object to the yellow one, and then you're inside the rectangular box. But everything is happening into the universe, which is the space of tempo distribution, the huge curly object, which is the dual of the smallest object in the game, which is the Schwartz space of rapidly decreasing functions. And what I tried to kind of emphasize over and over again, I was lucky to discover that space, that S0 is the natural and appropriate space, which is not a nuclear Fréchet space, but it is a Banach space, which allows you to build a pair of small space, which is contained everywhere, a dual space, which is S0 prime in the abstract notation, or I call it the space of mild distributions for some good reason. And everything is happening in between, and kind of halfway between the small and the big guy, there's the Hilbert space. So you have a space where the dual is big, and this Banach space is small, and in between you have a self-dual space, and that's of course a Hilbert space, and that's our classical L2 space. So I have, for your references, collected several references just to mention out of the study of these function spaces, mostly the modulation spaces. A lot of theory appeared, and meanwhile there's 2 books which appear this year on modulation spaces, and of course we have Charlie Gröchenick's book on foundations of time frequency analysis as our main reference. So kind of the goal is to say, at the end of the story, you have only to understand well how to work with S0, L2, S0 prime. And my way of explaining it is usually, it's like working with numbers. We have rational numbers, real numbers, and complex numbers. Rational numbers are good for computation. Well, S0 will be good to compute the inverse Fourier transform. We have the real numbers because they are complete. They are allowing you to define square root of 2 and other objects which are not available in the small object. Well, here we have Plancherel's theorem and so, but by taking limits from S0. And then there's the world of complex numbers, where we can do funny thing like exponential law implying addition theorem for cosine and sine. And that's like Fourier transform of a Dirac comb is only available at the outer level, and many other things. So we have a big universe, everything is okay. And if you're lucky that you start with one of those spaces in small spaces, you're getting out to the big spaces, you're moving into the original space by kind of regularization, then you get some nice results. So that's kind of the main story. I have tried to look up the papers that I have written in the last few years, mostly trying to explain how to go through this program. And I don't mention any one of this, but it's like a puzzle where you can see that certain aspects of the general program that I have developed can be kind of followed step by step. So it might be also for some of the students a topic for a seminar talk. Now, just to recall, the whole thing is very much based on the theory of amalgam spaces, which means you're gluing together local and global properties. And so I was just putting together a few references on this theory of amalgam spaces. So that's just for later reference. Now, looking back to some of the talks that are all available at the talk server, I realized that already 3 years ago at the ISAC conference, I was describing the idea of conceptual harmonic analysis with the claim that it's going beyond abstract harmonic analysis in the following spirit. I mean, my experience was that I was doing computations, I was doing Fourier series expansions, I was using ordinary Fourier transform, I was taking limits in certain function spaces. But at the end, it turns out abstract harmonic analysis only allows you to compare it, so to have analogy. What you see by a MATLAB experiment in the finite dimensional case might be true in the continuous setting, and then you go to prove it. But in reality, you would like to use the FFT algorithm to compute a continuous Fourier transform for a decent function. So this connection between the different groups and to see a continuous function as a limit of sampling values which are more and more, so this connection between the continuous and discrete world or even finite world, this is very little discussed in the literature, and this is also where these function spaces will be helpful. So as I said, the Banach-Gelfand triple is clearly a triple of 3 Banach spaces with nice embeddings. And it's also called a rigid Hilbert space. And rigid Hilbert space means for me a Hilbert space with additional structure. Many things which happen to be true just only for L2 may not be true in the 0 setting. So for example, if you take the critical Gabor family, it stands in L2. So it looks like you have enough building blocks when you take integer time frequency shift of the Gauss function, and you should get almost all of L2. Well, it's not all, but you are getting a very big set and it stands. If you do the same thing in S0, you would observe that the SAC transform, a continuous linear functional on that space at 1/2, 1/2, which simply means if you take an alternating Dirac comp sitting at a half-shifted version of the integers, that this is orthogonal to all these building blocks of this Gabor family. So you're missing one dimension. There is just not enough richness for this family in the 0 setting. And so you can look up Charlie's paper on doing Gabor analysis without inequalities, where you can recognize very well how this works also. So yes, these concepts are developed also with the goal of having a setting for conceptual harmonic analysis, but at the moment we are just working with we're starting from almost nothing. Now I would like to mention also that for me the natural setting is to work with Banach spaces of distributions. That's kind of a choice of tools, but I think it's enough to understand a large variety of Banach spaces. And then, of course, you have maybe decent functional spaces. But then, of course, you look at the dual spaces, and I'd simply call those dual spaces distributions, whether they are really only functionals on test function spaces in the classical sense, or just dual spaces of decent function spaces, that doesn't matter. And when we want to describe these problems in conceptual harmonic analysis, we have to do approximation in one or the other norm, maybe not in any norm, but in the weak star sense. And I also think one can well explain why this strange term weak star convergence is corresponding to something very, very natural. Also, when we want to do some computation, and this is an aspect that I don't cover in this seminar talk here, is the aspect of realizable constructive algorithm. We all know that there is a difference between abstract approximation theory, like the Weierstrass approximation theorem, which essentially says, well, it would be a scandal if the trigonometric polynomials would not be dense because we would reach a contradiction, or constructive approximation, which means, well, we can take the maybe for ordinary polynomials, Bézier polynomials or so. But a realizable constructive algorithm would say, well, but I could, for example, not invert uncountably many matrices. Even if it's described in words constructively, it has to be realized. So I would say, how can I reduce my algorithm to finitely many FFTs, matrix multiplications, and so on, and get a certain approximation for a given function norm? And again, this tells us we have to know which kind of function spaces are suitable for which kind of problems and so on. And there it's always good to have many function spaces, but not just the most complicated, but also the easy to use, which people can learn. It's plausible that engineers and physicists are not worrying too much about the details of mathematical analysis or so. And since Fourier analysis is a very old subject, it has developed for a long time more and more independently, I would say. Engineers understand that they have to use mathematical concepts, but the terminology already is quite far apart, and many things that are okay for a physicist or engineer are not okay for a mathematician, and vice versa. So what I would say is the scandal of our time in this field is that we are kind of focusing on completely different things. Mathematicians care for the existence of integrals. They are maybe not so much worried that you have different convolution rules for different settings, because they are saying we have to go to another group. But in reality, if you want to mix them to use one to approximate the other, you have to understand these connections. And again, this is not discussed in either mathematics or in engineering. So looking for what the engineers need, it's good to learn their problems and vice versa. So for the course, and I have a little bit of experience meanwhile with giving such courses, it's important not only to describe the techniques, but also to overcome the psychological problem of, well, it's too complicated, or we are doing applications, it's not necessary to be so pedantic and precise or so. So I would say the course as it is designed now and as the script is growing is essentially to say we should have a mathematically correct way of describing what the engineers need. I found a way to avoid Lebesgue integration theory, which looks strange, but it's quite possible, at the cost of a little bit more of functional analysis. We may remember that Lebesgue integration theorem, at least even according to the habilitation thesis of Radon, was the beginning of functional analysis, because when you have measure theory, you have nice Banach spaces with so-called LP spaces, and that's great. But we should not stay with this for the rest of our lives, so to say. That's my thesis. So I would like to show applications and so on. And as I observed, it's really requiring a lot of work, and there are even some open problems coming up. Now, maybe it's a short comment that I have developed a collection of pictograms for those various function spaces. So on the one hand, it should help you to get an idea how they are related to each other, because it's really confusing if you have 10 spaces at the same time. But on the other hand, I'm working on the proofs for the remainder without using LP spaces, except L2, of course. And this is possible because in the world of what I call Fourier standard spaces, and that's another topic that has to be discussed separately, S0 is the smallest and S0 prime is the biggest. So I would just say all the spaces that people use in Fourier analysis, well, not all, but big variety of those spaces are Fourier standard spaces. Just to tell you in words, it's all the LP spaces, all their Fourier transforms, all the amalgam spaces, local LP, global LQ, all the Fourier multipliers of LP spaces, all the convolution operators from LP to LQ, all the inverse Fourier transform of amalgam spaces of the form FLP-LQ. Sounds strange, but these are exactly the MPQ modulation spaces. So all those spaces, they are all Fourier standard spaces, and they have a very simple, decent structure, which can be better described if you say, well, I'm sitting in between S0 and S0 prime, so I'm in a sandwich position, nice embedding, and then I'm trying to prove my results using these things. Now, just to recall the operators that we are using all together, it's the ordinary shift operator, the frequency shift operator multiplying by frequency S, which is of course the same as shifting the Fourier transform by the S. And I prefer to use two different dilation operators. The first one is in the argument, so you're stretching if you make rho small in this case. This is how you get functions which are very flat if f of 0 equal 1. For example, if you take a trapezoidal function and you dilate it with rho goes to 0, you get huge trapezoidal functions which are good for summability issues. On the other hand, and these two correspond to each other on the Fourier transform, you can compress a function, and this is the Hans-Reiter M-rho operator, the area preserving dilation operator. Here, making rho small means you get big amplitudes and small supports. So rho to 0 makes out of a function with integral 1, or even a measure with total measure 1, makes the Dirac. So you compress everything until at the end, so to say everything is concentrated in one point, namely 0. And so these compressed, say, Gauss functions will be used as a replacement for the Dirac measure. So now I've collected a number of papers here, some of them by Jens Fischer. I had a lot of discussions with him. A recent upcoming article by Michael Anser is talking about Bibo systems. And essentially, they, as well as I, say, well, there is one big world of universe. Jens Fischer is using the temper distribution theory, which I think is not necessary. Michael Anser is observing that the books in engineering theory make false claim about the representation of translation invariant systems. So yeah, this is just kind of something where you can learn how applied people view the situation. So I just want to read this one statement, and I must say I don't know who was doing it, but it would fit as a statement of Walter Thirring, the big guy of theoretical physics in Vienna. It doesn't have to be sloppy just because it is applied. So, I mean, my attempt is to renew Fourier analysis in such a way that it can be useful for engineers and physicists, and still being mathematically correct. So you may enjoy reading this text later on yourself, and let me just come now to the applications. So maybe a last word about abstract harmonic analysis. Abstract harmonic analysis is working on different groups like R, RD, integers, torus, finite groups. Pixel images are functions on a product of cyclic groups. When you apply the two-dimensional FFT in MATLAB, you're taking the abstract group theoretical Fourier transform of this situation, and so on. But they are living on different groups. That's kind of the big difference. There's also a nice book by Gianfranco Girolamo about unified signal analysis, where he says, yes, real line, this is continuous non-periodic, set is discrete but non-periodic, torus is continuous but periodic or so, but you are just classifying signals as if a signal which is not decaying, like L2 functions on the real line, it has to be periodic with some period. And of course, this is not true. Just think of anything almost periodic, anything changing, like a piece of music. You can record it, you can compute the spectrogram, but it doesn't have function values almost everywhere. But from my understanding, it is a mild distribution, and therefore the whole theory is working well. Now, a glimpse on the history of the subject or so. The Siegel algebra is 0, S for Siegel algebra, Irving Siegel, and 0 for the minimality property, was introduced at the Winter School in 79 and published in 81. And the aim at that time was really to generate a decent Siegel algebra which can be defined on locally compact abelian groups. So it was the generality which was useful, and it was the minimality among all those Siegel algebras, whatever they are. Hans Reiter studied them a lot. They are the strongly character invariant ones. Now, in the modern terminology, you would say a Siegel algebra is a dense subspace of L1, which has the property that it has isometric time frequency shifts, and that they are depending in a continuous way also on the time frequency shift parameters. So it's a Fourier standard space as I see it now. Then in the contact with the engineers, it turned out that the right function spaces for many things in Gabor analysis were the modulation spaces. And so even before they were called Banach-Gelfand triple, these three spaces S0, L2, S0 prime appeared as those temper distributions, if you want. So you pull out from big enough repertoire those which have a short-term Fourier transform in S0, L2, or S0 prime. So and this was used, let's say in the paper with Georg Zimmermann, by always having parallel statements. Whatever is true for S1 with respect to Gabor coefficients in a little L1, you have L2 coefficients for capital L2, and you have L infinity here. And clearly L infinity is not allowing to approximate with L2 sequences. So you have to relax the convergence from uniform convergence in L infinity to coordinate-wise convergence. A good summary of the work on Banach-Gelfand triple at that time was done by Severin Bannert in his master thesis or so. Now, I think it's maybe just good to mention that I will define, or I define in the course L2, I just have done it last week in an indirect way, but the key property, if you would come from, let's say, Lebesgue integration theory, is that it's one of the spaces which not only is a Hilbert space and a Fourier invariant space, but it also has a double module structure. It's not a bimodule because the two module structures are not commuting, but you can multiply with decent continuous functions. C0, even bounded continuous functions are okay, and you can convolve. And the point is, if you have these two operations, you can regularize. Given any function, by multiplying it with a compactly supported function, you have a function with compact support, then you're smoothing it by convolving it with a smooth function with small support, or you're changing the role. So it's very easy to approximate everything in L2, for example, by elements in S0. Now, I just want to mention that's something I have not done in the course so far, that the terminology of Banach modules allows to express these things in a very nice way. So the role of the theory of Banach modules and the description of bounded approximate units or identities as replacement for the existence of a unit element is quite important in all my proofs. So we have these huge plateau functions which are taken as a replacement of constant 1 when you multiply them, but they allow to reduce everything to compact subsets. Or you're saying, I'm smoothing, so I'm more or less reducing on the Fourier transform side everything to a compact set. And then I work with band-limited functions. So, and it's always this slalom which makes Fourier analysis for me so interesting. It's like you have a straight line with where you think the skier is going down in a straight line, but he is doing an epsilon to the left, to the right. You're replacing a function by compactly supported. Then you go to the Fourier transform. Then you replace the Fourier transform by compactly supported. Then you do some weak star convergence, but after convolution, it turns into ordinary convergence. So these are the things which are quite fine. Just only one word about Lebesgue integration theory. Of course, no doubt, it's natural to assume integrability in order to define the Fourier transform as integral transform, to define in the pointwise almost everywhere convolutions. I don't even write it here. But even this good and perfect Lebesgue integration theory does not allow you to show that the convolution with the chirp signal, which is e to the pi t square, And remember the derivative of this, which is 2 pi t, is linear. So it's a linear frequency behavior. So it's in the audio case. And if you would see a spectrogram, and if I would have done it correctly, you would see a linear increase of the frequency. And then you say, oh yes, I think this should be a bounded operator in L2. And then you try to convolve such a chirp function with a sinc function, which is known to be non-integrable. And then for every x, the integral does not exist in the Lebesgue sense. So yes, Lebesgue integration is great, but it has certain limitations. Now, maybe I should spend a little bit more time on details about the motivation and how I get started in the course. One of the main motivations in the early encounter of convolution and Fourier transform for engineers is the course that also Helmut Bölzka is giving now, and which is running at most technical universities in the early stage of the engineering school, is we need to understand translation invariant linear systems. Well, mathematically speaking, these are linear operators, so we have the superposition principle, and the input-output relation mapping x to y has the property, if we shift the input, then we get the output, which has kind of the same shape as the original one, but also shifted by the same amount. Now, I'm only a little bit overdoing how engineers would prove it. Maybe they first do it for the discrete setting, and they say, yes, every signal is a sum of shifted unit vectors. So you take the unit vector at 0 and you prove a discrete version of this result. That's fine. But how do you prove it in a continuous setting? And that's, for me, almost like black magic. First, you're stating that we have to introduce the Dirac delta function. Well, this is a thing which is 0 everywhere except at 0, and at 0 it's plus infinity. Well, in a way it's nonsense because it's not a function. You shouldn't talk about pointwise values, but whatever it is, it has an important property satisfying the so-called sifting property. So you recover f, you can put any argument by writing it as a sum of shifted values of the Dirac impulse. I was putting the dot here because if I would put an argument, the second interpretation would not be so natural. So I'm saying, well, we have all these shifted Diracs, which are, of course, just the shift, the Dirac measures at u, and you're integrating over the whole thing. Now, what does it mean, really? And I think for me, it just means if you're asking what is the value of a function f at s, or if you want, you can say, what is the value of f after applying the identity operator? And the magic thing is, yes, you're getting the value at s. And so this is a magic, a black magic. And how can you do a reasonable result out of nothing, so to say? Because that's how they will use it. They would say the system T of f is, of course, because it's linear, it's compatible with linear combinations. So probably you can pull in through the integral, because an integral is a form of smeared sum. And then you say, well, I have the same formula here. So it's T of the shifted, so we should say it's T of the T sub u of d. So apply the system to the shifted Dirac. But we know that that the shift operator and the system commute. So we can say, no, either you write it as T applied to the shifted, or as I would like to do it, take the T applied to the delta, and that's of course what is called the Dirac impulse, and then you shift it. But then you say, oh yes, this looks like, if you write it out, that's exactly the convolution of the measure mu. So yes, this is a good explanation. Just take mu of delta and you get every operator is a convolution operator. Now, I don't even bother to try to explain it. Oh, sorry, and one more thing. On the other hand, you try to explain that if you go to the Fourier transform side, and if you've heard that ordinary convolution goes to pointwise multiplication, you expect that on the Fourier transform side, so you can describe the image of the system after on the Fourier transform side, but just multiplying with some kind of Fourier transform. So we have thousands of questions, and it's not as if as engineers kind of pretend that mathematicians can fix this approach. I think it's completely, I mean, I'm saying it now in a way which is maybe too strong, but it cannot be saved. So we have to try to kind of only take it as a motivation, and that's the starting point actually of the course. So I'm saying, well, we have to make sure that we really can put the delta into the system, and the good way to do it is to study Bibel system. Bibel system are bounded input, bounded output systems. So the formal definition is in the middle of the slide here. We're talking about a bounded linear operator, where every function vanishing at infinity, which is a Banach space with the subnorm, is mapped into another element of this space. So the input-output relationship is by a bounded linear mapping on this space, and the mapping is supposed to commute with translations. And then the claim is there is some functional which is describing this, and it means the output at any point y, maybe y is not a good letter, is obtained by taking the input function, flip it, that's the flip operator, shift it to the amount y and apply the mu. I would also like to say, well, you can move all the flip and the y to the other side, and then you would say, no, it's a moving average. Take the mu, instead of flipping the f, flip the mu. Then you find it's a moving average. And you take that moving average and it's moving along the y. So actually, the tyf flipped is the same as taking the same as t minus yf, and the whole thing flipped. So I can write this as mu flipped applied to t minus yf, and that means it's like t of the flipped mu measure applied to f. So it's really every such thing is just a moving average, and that's quite nice. I even explained this at the beginning of the course by using, instead of C0, the space of cubic polynomials, because it's such a nice and simple vector space, which is 4-dimensional or so, but clearly if you write down explicit description of linear functionals on the space of polynomials like point evaluations, integrals, and other things, derivatives, you see there are a lot of such things, and you just move them around. And the easiest case is, of course, integrate over an interval of length 1. Then you really have a moving average, and otherwise you have other things which I call still moving averages. Now, what is the mu here? The mu is just a bounded measure if you take the literature, or for me it's a linear functional. So it's just a bounded linear functional, something that's acting nicely, like a Dirac, like some other things. And the norm, of course, of a bounded linear functional is given by the subnorm, whereas the operator, the convolution operator, is the relative enlargement that you have between input and output. So you look at the possible size of all the input-output vectors given input vectors of norm 1. And that's the sup, and the idea is to prove, and that's what you have to do, this is isometric. Now the trick is, if you look at all these systems, it's invariant systems, it's obvious that they are closed under composition. Two operators put together are again bounded, and again, by iterated commutational law, they commute. So if you give me two bounded measures, I produce two convolution operators by this rule. Then I compose those, and then I get back some system, and that can be represented by some uniquely determined measure mu, and that's what I call mu1 convolved with mu2. Now, this is very nice and can be easily checked that if you take Dirac measures, the corresponding linear operators are just translation operators. So it's clear for linear combination of translation operators, for absolutely convergent sums, the so-called discrete measures, everything is fine. But unfortunately, you don't reach arbitrary measures by limiting in the norm of the measures space. And that's why discretization have to come in, and weak star approximation is important. I'm not going into the details, but I would like to say there's a trick to approximate probability measures by histograms. You all know these pictures where you see the Gauss curve, then you see experimental data and the fine histogram, which looks very much like a step function approximating the Gauss curve. I'm doing exactly this in a discrete way. So if you give me a partition of unity, which is such a family, so fine, now for technical reasons, I want to make it smooth, but you can also think of rectangular functions from n to n plus 1, which are a little bit smoothed only if you prefer it, then you're very close to the bins of a histogram. And then what you're doing is you're discretizing it. The psi is one of these functions here that we have here. And then you ask, how much mass do I have? So what was the experimental share of your findings in this bin, more or less? And you put a delta here. The best way to understand that this is a decent form of approximation is, of course, to take the distribution function. The Gauss function would have a smooth ramp, whereas these approximating things would have a step approximation, which of course follows the ramp very closely, and that's the right way to do. And then you prove that these convolutions are weak star continuous, so you can verify that the convolution that we define for bounded measures is the only reasonable extension for the convolution for discrete measures. But by the composition of systems, it's much easier to describe that it exists and afterwards justify this uniqueness property. Now, one of the important things actually in the proof is, how can I prove that the convolution of a bounded measure with a C0 function is going to 0? And for this, you need that the bounded measure is approximated by a compactly supported measure. Normally, you would use sigma additivity of the measure, but this is not available because I'm not doing measure theory here. So I have to prove, but it's not very difficult actually, that the sum of the localized measures, so maybe I should say mu times a function applied to f is just an adjoint relationship is like mu applied to psi k times f. So it's a localized version, it's another measure, and the sum of the pieces has exactly the norm of the overall. So an inequality that left-hand side is dominating, the right-hand side is easy, the converse is a little bit trickier. So here you have the rule. Okay, and now with this trick, we also can extend the action of a bounded measures, not only C0 to, but also to bounded measures, which is important because then we can say, well, we can feed in even pure frequencies, these characters, e to the 2 pi I, and then you will find out that they are all, all these pure frequencies are eigenvectors, joint eigenvectors to all those convolution operators. And that's a great message. And of course, you hope that we're diagonalizing all these operators by the Fourier transform, which is a very good idea, but technically you have to work quite around this idea. What is mu hat? And it's just the application of, we define mu hat by saying take the measure applied to the bounded continuous function, which is the conjugate of this here. You see in Fourier analysis, we have a minus, and therefore it's appropriate to have this, but it's also quite easy to prove this. And one of the standard rules that I'm teaching all the time now is if mu is a Dirac measure, it's just the exponential law. If mu is a discrete measure, you get it by summation. If mu is a general measure, you get it by taking limits in the appropriate way. Okay, now we have not used integration theory, so we have to see how we can get L1. And the trick is, of course, we have to take the bounded continuous function. So C0 is continuous function with compact support in RD, complex valued continuous functions. They're inside the measures, but they're also inside C0. Now we look at them inside the measures by saying, well, they are densities. And so if you apply it to a C0 or CB function, you just multiply f with k of x and you integrate the resulting function. And actually you can do it with Riemann integrals. Now you have to work a little bit to find out that the functional norm of the measure induced by the nice function is just the ordinary L1 norm, but this is something that you can write with the Riemann integral. And then, of course, we have to find out how we can use now the mu applied to the delta. So we have BIBO systems which allow to feed into the system a priori C0 function. After this decomposition of measures, we can feed bounded continuous functions, but then we need the following observation. If you have any operator like convolving with a measure nu, so that's an operator from C0 to C0, we can define the adjoint operator, which is given in this way. The adjoint operator acting on a measure mu, so I call it star adjoint, is just defined in this way. Then we have to work a little bit, again, trying to do it for Dirac measures, limits, and so on, to find out, yes, there is this internal multiplication that we have done already, but you have to convolve with the flipped operator. After all, this is not very surprising if you do it for functions. But now it means that the joint operator, so it's an exercise to show that if something is a bounded operator going from C0 to C0, the joint operator is bounded on the dual space, so from bounded measures to bounded measures, but it's also weak star continuous. That's very important. And so what we can say is that if we look at the situation that engineers are doing is, well, convolution with every measure is also as bounded if and only convolution with the flipped measure is bounded, because flipping is an isometric operation on the bounded measures. So there's no difference. Now, every operator is a convolution operator, which is the convolution with the flipped version of the mu that is doing the flip job. And therefore, you are having a weak star continuous situation. And that's what you see all the time when engineers are demonstrating their result. They say, well, you see, you put the Dirac sequence, which is compressed the rectangular functions, into the system. And I would say, yes, we approximate the Dirac, but not in a pointwise sense, but in the weak star sense. Clearly, of course, the box functions go to the Dirac delta. And if you have a t, which is now the extended t, this is the version that is working from MB to MB, but it's compatible with the original version, and therefore I'm using the same letter. This can be commuted. So you can say, well, it's the same as taking the weak star limit of what's happening on the output side. But on the output side, I know that t of some decent input, I mean, this is in C0, is just mu convolved with this. But then we say, yes, this is an approximate unit. This will go in the weak star sense to the measure mu, because if you move again this to the other side, it's acting nicely on these things. So it's a way to justify for BIBO's system that you can really do what engineers were doing. Now, I just want to kind of give you a very quick overview over the rest, which means, well, for now, the situation is nice. You have learned signals are in C0, that convolutor are in bounded measures, but they are having a common space which is bounded continuous, compactly supported continuous functions, but it's not good to, because they are not one contained in the other. And also they are not Fourier invariant. To overcome the first problem, one may use what is called Wiener algebra. The Wiener algebra, it's one of the many Wiener algebras. The one which appears in Hans Reiter's book on single algebras as an example. So you take the continuous functions which have a finite upper Riemann and sum taken over the full RD. So you make boxes and you take the super of every box. So you can take a grid over the plane, for example, to see that this is a nice subspace. But that again is not Fourier invariant. Then you can say I'm taking only those functions where the function and the Fourier transform is in the Wiener algebra. And it was hard work and problem solved by Victor Lozat in the 80s, that this space is really slightly larger than S0, but technically it's more difficult to handle because you have two separate conditions. And so it's interesting to find out that you have to first, and that's what we have done in the course so far already, you have to introduce the Fourier algebra. So we know what L1 is inside the bounded measures. We know what the Fourier or Fourier-Stieltjes transform is. And so we take this, we have verified Riemann-Lebesgue lemma. This is a subspace of C0. You can take the norm with you because it's inverse. The inversion theorem allows you to have injectivity, and you prove that this Fourier algebra defined in such a way allows convolution. This is quite important. And then I'm doing the old construction of zero by saying, well, within C0, doing the absolutely convergent decomposition, we get the Wien algebra. And if we take locally not the sup norm, but the Fourier algebra norm, so you require a little bit more smoothness, then you're getting a space which is kind of decent. Now, this was the space which was the smallest space, and it turned out that you can describe it in many different ways. And so what we have done recently in the course was to prove that it can be, you're allowed to convolve. That's because all these things are kind of controlled by pieces. L1 is cut into pieces, S0 is into pieces, so it's fine. It's rather easy to the pointwise multiplication. And the hardest work in this approach was to prove that you get a Fourier invariance. We always have done already Poisson's formula, which is necessary to connect the discrete with the continuous setting. And we also have just discussed the question of describing, that's the last statement, the norm by an equivalent norm using the short time Fourier transform. So essentially it's the idea, instead of doing a discrete composition where you use shifted versions of a trapezoidal function, for example, we do a continuous integral. And that integral could be a Riemann integral to see that you don't have to invoke Lebesgue integration at this point. So yes, you could define S0 as all those smooth, or let's say continuous functions where the localized version of the Fourier transform have a Fourier transform in the Wien algebra, for example, and everything is only with Riemann integrals, and you would have the same space. Now, once we have this, and especially the Fourier invariance, we can define the Fourier invariance, the Fourier transform on the dual space, and that's the starting point for a lot of things that allows to cover classical topics and show that this wider theory is including the classical one. Also here you see that the Fourier transform, the extended Fourier transform, is an extension of the ordinary Fourier. Well, you have to verify, but the fundamental relation of the Fourier transform that if you take an ordinary distribution coming from a test function, then this is a valid statement, with this being interpreted in a classical way. And then you can turn this into a definition, which of course is consistent. So we have the only weak star continuous extension of the ordinary Fourier transform, because we have meanwhile already shown that the zero is weak star dense in zero prime, and that this definition turns into a weak star continuous mapping, because it's in a joint clearly of the ordinary. We are at the step of proving Shannon's sampling theorem to use the fact that the Dirac combs for arbitrary lattices are in the dual space, of course. Therefore, they have Fourier transforms, and by Poisson's formula, of course, these are according Dirac combs living on the orthogonal lattices. In this way, you can define that periodization corresponds, on time side, corresponds to sampling on the frequency side, and vice versa. And yeah, so the Poisson formula is replaced by the formula that the standard Dirac comb on the integers ZD inside of RD is the Dirac comb. This is kind of, aside from the Fourier invariance of the Gauss function, one of the crucial statements in this approach, of course. Now, one other thing which I have done recently is to check that, which is of course doable in the tempo distribution world of Laura Schwartz, but I don't need it. So I was proving that periodic discrete measures, which are of course finite linear combinations, I think, yeah, I've not written it here, yeah. Periodic and discrete signals even in a multidimensional setting, can be viewed as linear combinations of Dirac comps. So there's a coarse periodicity comp or lattice, and you're doing a finite linear combination along some subdomains, fundamental domain. And in this way, you find out that a periodic discrete signal has a Fourier transform which is discrete and periodic, but if they are compatible on the time side, they will be compatible also on the Fourier transform side. So also there you need exactly as many coefficients. And the question is, how are the coefficients describing the original signal in the time domain connected with the signal, with the coefficients needed for the Fourier transform? Well, and then you have to apply that rules. The translation of one Dirac comp to another is going into multiplication. And then the multiplication of a Dirac comp is reduced to a multiplication of deltas. And that means you have to sample those frequencies at the lattice points. That's giving you exactly the formula of the discrete Fourier transform in one or many dimensions. And of course, in practice is something that you would write down directly or so. There is one paper, meanwhile, where I tried to discuss a little bit how other classical questions, especially questions about summability, can be dealt with using S0. So Ferenc Weiss has checked that all the summability kernels that he knows, and I think he's the world expert on this, they are all in S0. Also, Charlie had a paper in '96 showing that if you have a counterexample to Poisson's formula in a certain setting of weighted amalgam spaces, you find it in his book, then it's because those spaces are not contained in S0. So S0 is kind of the smallest space in the zoo of spaces, which I call Fourier standard spaces, but it's also bigger than most of the spaces used for which kind of to describe nice functions. So it's a very simple, very space of nice functions. And at the end, I would like to mention that, of course, you would like, in the spirit of conceptual harmonic analysis, to compute the Fourier transform of a function in S0 by applying the FFT to the samples of this function. And there are two papers. One I did with Norbert Keiblinger, to say, well, if you take a piecewise linear interpolation of a function in S0, eventually you will approximate it. Actually, it's not important that it's piecewise linear. You can take any BUPO, any smooth partition of unity, then you have quasi-interpolation operators. But if you compress them, you're doing finer and finer. Approximation is not just uniformly convergent, but it's convergent in the S0 norm for every f in S0. The proof actually was going through the fact that you can put everything on the Fourier transform side and get the analysis done on the Fourier transform side. And Norbert then was going on to say, well, if you compute a Fourier transform, what you have to do is sample a function fine enough, long enough, then take the FFT, then assign these values in a correct manner back to sampling values of a function, do piecewise linear interpolation or quasi-interpolation, then you will get a finite linear combination of elements from S0 if your BUPO is in the Fourier algebra, and that is convergent to the f hat which exists by the Fourier transform. So this is really a nice tool, and I think one should try to quantify it and get better results knowing that you are in a subspace compactly embedded into S0, for example. One should get rates. Now I think my time is over, and therefore I would like to mention that you will find already now the slides for this talk at this page. Give me a few minutes to do the corrections. And if you have questions, we can use the chat and we can also do this. I'm stopping the recording now. Thank you.